Hello again, this is Galen Pickett, Cal State University of Long Beach Physics, Physics 151. So again, I want to talk to you about, in Chapter 4, Section 8, the kinetic friction approximation. So this is the kinetic friction approximation. So, friction in the ancient world was considered to be one of these fundamental interactions. Every piece of matter had a fundamental interaction that caused it to slow down, and that is not what we know today. Friction is a consequence of the fact that matter is made from atoms. So here is a block, a sketch of a block that's sitting on a table, and I'm going to blow up this section right here. So the blue is showing you the table. So there's the blue table. Where the block is actually contacting the table, the atoms of the table are being slightly depressed. It's made out of these atomic level springs, and they're being pressed downwards because the block, the surface of the block, is also composed of matter, which is just the weight of the block is pushing this thing down. So the surface actually indents a little bit, and you can see the blue surface being pressed downwards away from its equilibrium. That gives rise to a force, what we call a normal force, that would cause the block to be moved away from the surface. But because the surface has been depressed a bit, there's also going to be a lateral force. You see how it rises up here, it would continue up here to the rest of the surface. There's also going to be, because of this block, this edge here, a lateral surface, or a lateral force if we decided to move the block to the left or the right. And that lateral force we call the friction force F. So the harder you press the surface downwards, the deeper this impression is, and the bigger this lateral force is. That gives rise to this kinetic friction approximation, which gives us a relationship between the magnitude of the friction force and the magnitude of the normal force. The constant of proportionality is called the coefficient of kinetic friction, mu k. And so I've got a force over here, a force over here. The mu k is a dimensionless number. And I want to let you give you an example of how you could use that. So here's an object that has got a mass m. Let's say it's got initially, it's got some initial velocity v0, and after a time delta t, I'm putting some force on it, some force t. I want to know what its final momentum is. But the surface does have some real characteristics. This is now a friction surface, not a frictionless surface. So I'm going to take this problem and turn it into a problem-solving strategy. So the director says we're going to use the momentum principle and the friction approximation. How do I know that's the momentum principle? Well, I'm being asked for what is a momentum. I have an initial momentum, this is m times v0, and if I can figure out what all the forces are, I know what the delta t is, I'll be able to figure out what the final momentum is. But I also need the friction approximation, because one of these forces is going to be the friction force. So what do I know in this problem? The givens. Well, I know what the surface is, so I know what mu k is. I know what v0 is, I know what m is, and I know the force that I'm using with. And I think there's one more implicit known in here, that p final y, the y component of the final momentum, is 0. Because the block is going to stay on this surface. If it had any y component, it would leave the surface, and it's not going to do that. So that's all stuff I know. And let's say I also know what g is. Unknowns. Well, I don't know what the normal force is. I'm not given that. I'm going to figure it out, but I don't know what it is, and I don't know the friction force. Those two things I do not know, and I do not know p final x. And that is the thing that I'm being asked for, so that is that's what we've got. So the director's level job is done. Now the investigator takes over. So the investigator is going to need to first define what the system is. So let's say the system is the block. So the surroundings are the surface, and that's going to give a normal force and a friction force, and the earth itself, that's going to give the weight force. Once I've got the system and the surrounding set, I can make the net force diagram. So there is the system. It's got a mass m. And now I put all my interactions on this. I've got a normal force, I've got a weight force, I've got my force, so I forgot to put me in there. Me, I'm part of the surroundings, and I've got a friction force. These are all vectors. So this is the purpose of this is just to figure out what are the net force, what is the total force from the surroundings on the system, and now I can write down the momentum principle. M times V final is equal to M times V initial plus the net force, which is, just read it off in this diagram, N plus F plus T plus W. And that is, I'll call this equation number 1, but it's a vector equation. It's got an x component and a y component, so it counts as 2 equations. I've got 3 unknowns and 2 equations, so I need one more idea, and I have not yet used the friction approximation. So I will now, that will be my equation number 2, F is equal to mu k times n. Now this is not a vector equation, this is a relation between the magnitudes of these vectors. So now I've got 3 equations and 3 unknowns, and now I can solve it. So if I look at the x component of equation 1, I have m times v final x is equal to m times v initial x, which is given. So I'll put that in a second. I add to that the x component of the normal force, which is 0. Then I add to that the x component of the friction force, which is minus f. The friction force points in the minus x direction. X, y. The tension force plus t, and the weight force plus 0. So I get m v final x is equal to m v0 plus, and I'll rearrange this, t minus f. So there's still two unknowns in there. Let's see what the y component of equation number 1 looks like. So I have 0 because the y component of the final velocity is 0. And that's equal to 0. The y component of the initial velocity is 0. I add to that the y component of the normal force, which is just n, the y component of the friction force, the y component of the tension force, and then the y component of the weight, which is minus mg, and that tells me that n is equal to mg. The normal force is just equal to the weight. Even though it's moving, the normal force is equal to the weight. I'll put this into equation number 2, and that tells me that the friction force is mu k times mg, and now I'll put this one back up into the x component there. So I get m v final x, which is the thing we're looking for, is equal to m v0, oh, this is all times delta t, plus delta t times t minus mu k mg. And there's the answer we're getting. So now the skeptic will check what's going on. First, the units of m v final should be kilogram meters per second. This one is exactly a kilogram meters per second. Let's check out this next one. So I've got seconds times, and both of these things is a force, times newtons. So that is kilogram meters per second plus second times, a newton is a kilogram meter per second squared. So those things cancel off. So I get kilogram meters per second. I've got the right units. And there are no unknowns left in the answer. If I had, say, the friction force or the normal force still in the answer, that would not work out. Those aren't given in the problem. The only stuff that's in this box are stuff that's in the knowns list at the beginning of the problem. Now let's check the behavior. We could have m v final x is equal to m v0. This would be a special case in which the v final is equal to the v0. So the object moves, but it moves with a constant speed. And that sounds a little paradoxical. We have to decide if that's a problem. Because this kind of motion, I'm going to give you its breadcrumb data, it would look like this. It would look like the object is moving without any interactions at all. And if that's the case, well, don't you need a force to be moving? And the answer is exactly not. No, you do not need a force to be moving. You need there to be no net force in order for this kind of motion, this non-interaction motion, to happen. So what we've got is the tension force and the friction force are exactly canceling. And we'll have the normal force and the weight force also canceling. So we've got 4 interactions here that add to 0 that give this motion that looks like there was no friction in the first place. So that is actually, that matches that reality check.